One of the most interesting tasks in chapter 8.1 is, given a sequence of numbers, can we come up with a formula for them based on n, kind of like x? Let's talk about some helpful facts before we do that. What is 0 factorial? Your instinct might have said 0, but remember it's 1. So 0 factorial is 1, not 0. What is 0 to the 0? In earlier calculus classes, you probably said that's actually undefined. It depends on, like, if you have x to the y, how is x approaching 0, how is y approaching 0. So technically it's undefined, but here in chapter 8, we're going to just say that 0 to the 0 is 1. We're going to say that anything to the 0 is 1, even 0 to the 0. So it's generally 0 to the 0 is undefined. It's an indeterminate form, you could say. But just for convenience, we're going to say it's 1. How does negative 1 to the n behave? Let's think about that. When n equals 1, negative 1 to the 1 is, well, anything to the 1 is itself, right? So this would be negative 1. When n equals 2, negative 1 squared. Anything squared is positive, so that's that. Any real number. N equals 3, negative 1 cubed. That'd be negative 1 times negative 1 times negative 1. Two of the three negatives cancel, and you get minus 1. When n equals 4, negative 1 to the 4th. What would you say that is? That's negative 1 squared times negative 1 squared, so that's 1, etc. So this is going to be, let's write it again here. Negative 1 to the n is what? Negative 1 sometimes and 1 other times, and it's negative 1 when n is odd. And it's positive 1 when n is even. What if you want something that works the other way? But if you want something that's negative 1 when n is even and 1 when n is odd, well, you have a few options. You could say negative 1 times negative 1 to the n. Just take whatever this was and flip its sign by multiplying by negative 1. Or you could think of it as negative 1 to the 1 times negative 1 to the n. So you could say it's negative 1 to the n plus 1. That way, if n is odd, n plus 1 is even, and so you're flipping between rows here. Or sometimes it's helpful to say negative 1 to the n minus 1, which also flips odd to even, but sometimes that's just more convenient. We have to be careful to not do is mix up negative 1 to the n with negative 1 to the n like that. What is this? It's negative 1 to the n, which is always negative 1. So when we're writing negative 1 to the n to get that alternating sign, we really do have to put parentheses around the negative 1. All right, so anything else that's handy here? If I wanted a way to get just the even numbers based on n just goes 1, 2, 3, 4, 5, it's going to be all the evens, all the odds. Is there something we can do to n to get just the even numbers? Well, if you take any integer and multiply by 2, you're going to get an even number, right? So 2 times n will always be even. Let's even if n is odd. What if you want just the odd numbers? Well, every odd number is just one larger than an even number, right? So you could say 2 times n plus 1 is always odd. Or you could say every odd number is one smaller than an even number. So you could say 2 times n minus 1 is always odd. So you'll see either of those expressions depending on whether we want to start at n equals 0 or n equals 1, etc. But those are some handy ways to get just the evens or just the odds. Let's try to come up with a formula for this sequence. We said before this is powers of 2. So what would be an obvious first guess? We might try 2 to the n. Well, at n equals 1, what is 2 to the n? It would be 2 to the 1, which is 2. And then at n equals 2, 2 to the n is 2 squared, which is 4. So that would be saying that this is the n equals 1 term, and that's the n equals 2 term, and that's the n equals 3 term, which seems to be working okay. But then what would this be? That would be the that would be the 2 to the 0 term, which would be starting with n equals 0. So this would be okay if we were starting with n equals 0. So let's write that. This is okay if we start at n equals 0. But if we want to follow the default in this section is starting at n equals 1, then we'd have to modify it. We'd want something like 2 to the n times something or something like that to be 1. So we can make a little table even. When n is 1, 2, 3, a sub n would be 1, 2, 4, like that. So what could we do? We could notice that each of these is 1 power of 2 less than what we kind of figured it would be. So we could try something. We could try a sub n equals 2 to the n minus 1. Say just take the previous power of 2. Does that work when n equals 1? So if n equals 1, we get 2 to the 1 minus 1, which is 2 to the 0, which is 1, which is what we want. If n equals 2, we get 2 to the 2 minus 1, which is 2 to the 1, which is 2, which is what we want. If n equals 3, we get 2 to the 3 minus 1, which is 2 squared, which is 4, which is what we want. So we seem to be on the right path. So saying this is powers of 2 is great, and that would say this is the n equals 0 term, n equals 1, n equals 2. But if we wanted to start at n equals 1, we'd have to adjust it a little bit. How about this sequence, which we looked at before? Can we come up with a formula involving n for it? Well, let's try defaulting to n equals 1 here at the start of our sequence, n equals 2 there, etc. That's always a good place to start. Looks like we've got 1 over n, right? 1/3, 1/4. So let's try 1 over n. Does that work out here for the first term? Well, that would be 1 over 1. So that seems to work because that's 1. And then what are we going to do about the negative every other term? We could say times negative 1 to the n. Let's give that a try. Let's say here's n, here's a sub n, 1, 2, 3, etc. So if I plug 1 into this formula, I get 1 over 1 times negative 1 to the 1. Negative 1 to the 1 is negative 1, so I would get negative 1. Here I'd get 1 over 2 times negative 1 squared. That would be positive, so I'd get 1 over 2, but I want negative 1 over 2. So this isn't quite working. What can we do to fix it? So let's try 1 over n times negative 1. So the problem was we got an odd number here, but we needed an even number to get negative 1 to an even number, which would then be positive. So how can we turn any odd number to an even number and vice versa? We can just say n plus 1. We could have also done n minus 1. So let's try that. So when n is 1, we'd get 1 over 1 times negative 1 to the 1 plus 1, which would be positive 1. When n is 2, we'd get 1 over 2 times negative 1 to the 2 plus 1, which is 3, and negative 1 to the 3 is negative, so I'd get negative 1/2. So that seems to be working. There's a few other things we could have done, like we said, could be n minus 1, could be negative 1 to the n, and then throw a minus out here. That would also be fine. Let's try another that we had before, 4, 0, 4/3, 0, 4/5, 0, 4/7, 0, etc. So go ahead and try to come up with a formula based on n there. Again, we default saying that's n equals 1 gives 4. But here we have alternating behavior. When n is even, we get one thing, one kind of pattern. When n is odd, we get another kind of pattern. So it's okay to specify that in a formula like this. We could say a sub n equals, and have two branches. One would say if n is odd, then what are we getting? Like 4 over n, 4 over n, 4 over n. Does that even work here when n equals 1? We'd get 4 over 1, which is 4, so that's great. If n is even, then just 0. So that's a perfectly good way to specify a sequence to say if n is this kind of number, do this. If n is that kind of number, do that. Later on, we'll see a more complicated way to do things. That's especially helpful when we're doing sines and cosines. But for now, you can specify things like that. Here's a quick overview of the rest of chapter 8.1. There's the definition of limit for a sequence. There's also various limit theorems. There's definitions for sequences being bounded and unbounded, and then the properties of being monotonic increasing or monotonic decreasing. If something is monotonic, we can also say it's monotone. It's related to the word monotonous, like if someone is talking in a plain voice like this and not really varying their expression, we would say that's monotonous. But in this case, it's monotonous because it's doing the same thing all the time, increasing, or because it's doing the same thing all the time, decreasing, rather than just staying flat and level like a monotonous kind of voice. I don't really have anything to say to add to the textbook for all these things, so just go read them and apply them in the homework problems.